Welcome to myprojectbazaar.com. Let me discuss about the process improving the separability of motor imagery EEG signals using a cross-correlation based least square support vector machine for brain-computer interface. Let me discuss about the project improving the separability of the motor imagery EEG signals using a cross-correlation based least square SVM for brain-computer interface. The EEG signals were taken from the brain-computer interface machines and they are collected and loaded in the system. The loaded signals were then pre-processed using some wavelet filters in order to remove the noises from them. Then the features are extracted from the signals using the cross-correlogram of the input signal and the reference signal. The cross-correlogram signals convey greater signal information and consist of low-level noises compared to the original signal. A cross-correlogram contains information about the frequencies which are common to both waveforms, one of which is usually the signal and another one is the reference. The values that we got by applying the cross-correlogram becomes the feature of the signal. The features were extracted for all the signals in the database and the true label for all the signals were set as. This process is called as training. Without training, the classifier cannot classify the signals. In the testing phase, the features were extracted for the input signal that we give. The extracted features were selected using genetic algorithm. Both the test feature and the train features were selected using the genetic algorithm. The features that are not repeated always and the features that have high value data, that features were called as the best features. The best features were identified by GA and the identified features were selected and they are saved separate. Then finally, the least square support vector machine is used to classify the EEG signals. Least square support vector machines are the least square versions of the support vector machine, which are a set of related supervised learning methods. They analyze the data and they recognize the patterns, and they are used for classification and regression analysis. This finds the solution by solving a set of linear equations instead of a convex quadratic programming problem for classical SVMs. Basically, it categorizes the train image features based on the similarities between the features and then arrange them in a single category. Then it compares the test image feature with each category, and with that the data is the least square support vector machine is identifies the target and give the results. The obtained values, based on the obtained values, the signals are classified into abnormal or normal. Let me see the flow of the process. Improving the separability of motor imagery EEG signals using a cross-correlation based least square support vector machine for brain-computer interface. Initially, the EEG signals were collected from the brain-computer interface machines that generate the EEG signals from the persons. The generated EEG signals were saved and they are used for our process. The input EEG signals are initially pre-processed. The pre-processing of the signals refers to the removal of the noises from the signals. Using the filters, the noises in the signals were removed. The signals are separated into channels and pre-processing is applied. The noises in the signals will affect the performance of our process. So in order to improve the efficiency of the process, we employ the pre-processing step. The pre-processed signal is then cross-correlated. Cross-correlation signals convey greater signal informations and consist of low-level noises compared to the original signal. The cross-correlation contains information about the frequencies which are common to both waveforms, one of which is usually the signal and the another is a reference wave. Based on these values only, the features are extracted from the input signal. Similarly, the database containing several signals is trained based on the features extracted from them. Then the extracted features were selected. We select the number of features from the original extracted features using genetic algorithm. The features that are not repeated always and the features that have high value data, these features are said to be the best features. The best features were selected using the genetic algorithm and from the both training and the testing features, and they are saved. The saved features were only given to the least square support vector machine classifier. The least square support vector machine is used to classify the EEG signals. The least square support vector machines are least square versions of the support vector machines which are related supervised learning methods that analyzes the data and recognize the pattern and which are used for classification and regression analysis. This finds the solution by solving a set of linear equations instead of convex quadratic programming problems for classical SVMs. The least square support vector machine compares the test image feature with the train image features and provide the label of the feature that matches in the train feature. Based on the label, we are classifying the signal into normal or abnormal. The performance analysis is done by measuring the accuracy of the classifier and comparing it with the previous algorithms that are used in order to classify the EEG signals. Thus, we are identifying the input signal as normal or abnormal based on the cross correlation features extracted, and we select the features using the GA algorithm, and finally we are classifying this using LSSVM classifier. Let me see the execution of the process, improving the separability of motor imagery EEG signals using a cross correlation based least square support vector machine for brain computer interface. If you want to run the code, select main.m file which is present in the source code folder. Right click it, you will get these tabs. Select run file in order to run the code. You will get this guide window. This guide window contains the user interfaces that is needed to run the program. First click on the input signal button. This will show you some signals and you can select any one of the signals from them. When you give the signal, the selected signal is plotted in the axis. Then we perform denoising using wavelet transformations. So we are denoising the input signal using the wavelet transformation so that the resulting signal is clear without any noises. Then we are extracting the features from the signal using the cross correlation. The cross correlation compares the signal with the reference signal and find the peak values obtained from them, and the values were saved as features. Then we are performing the classification of the signal. For classification, we need to train the database. So first we are training the database, and then we are selecting the obtained features from the extracted features. The selected features are then passed into the LSSVM classifier. The LSSVM classifier classifies the signal into normal or abnormal based on the true label provided and the training and the testing features. So the input signal is classified into normal based on the provided categories. Thus, we are providing a system which identifies the signal based on the features extracted as normal or abnormal. The EEG signals were obtained from the brain computer interface machines so that we can classify the signals based on this features extraction process. Thank you.